All right, everyone. So my name is Piero Molinari. I'm a master's student in CBPF in Rio, and I'll be talking about a work I've been doing with my advisor, Nelson, and a former student of his, Paola. So this is a quantum cosmological model. So I will give a very brief theoretical background and explain some of its features and results we've been getting recently. And so the first method of quantizing gravity is the canonical one, where you find the Hamiltonian of general relativity and quantize it. And this can be done in the ADM decomposition formalism, where you consider a time foliation of three-dimensional surfaces, which will be evolving in time. And by using this formalism, you can rewrite the Einstein-Hilbert action of general relativity. And from this, you can follow the standard procedure and obtain the Hamiltonian density, and then quantize it and obtain the Wheeler-DeWitt equation. Now, this equation has some mathematical issues, namely the normalization of the state functional and factor ordering and some other things. But we can overcome these issues by considering the mini superspace models, which is the case of cosmology. But in quantum cosmology, we have to use a different interpretation of quantum mechanics. We stick here to the Bohmian approach, in which particles have a definite trajectory in space-time, and they are guided by the wave function of the system. The quantum effects are encoded in the so-called Bohmian potential, and this approach is very good for cosmology because, contrary to Copenhagen interpretation, there is no need of a classical external observer to the system, and the notion of probability arises necessarily only for subsystems. And when you apply this formalism in cosmology, you generally find bouncing models, which are non-singular models of the universe, and they happen to solve two issues, which are also solved by inflation, namely the particle horizon problem and the flatness problem. So by considering the simplest case of a Robertson-Walker spacetime with a perfect fluid, you find a Hamiltonian of this form, which can be readily quantized using a Schrödinger equation, essentially. And by solving it and assuming a Gaussian initial state, you can follow the Bohmian procedure and obtain a bouncing trajectory for the scale factor. So it's non-singular, and it reduces to the classical evolution for late times. We can generalize these models, which is what we have done by introducing a momentum factor to the wave functional and break this symmetry with respect to the time of the bounce. So introducing this momentum term and evolving the wave functional using a non-unitary propagator, we can obtain this expression for the final wave functional. And of course, this non-unitarity is allowed in the Bohmian setting because of what I said about probability not being fundamental to the system as a whole. So from the phase of this wave functional, we can compute the guidance equation and then find the trajectory of the scale factor, which after some redefinitions and comparison with cosmological observables, we find that it can be written in this general form here, involving this parameter y, which is related to p of the wave functional. And we can choose to have either a subtle contraction or a subtle expansion, depending on the sign of this momentum factor. So choosing it to be negative, we have a very subtle contraction followed by an accelerated expansion, and then a classical decelerated expansion for the scale factor. So here we have the conformal Hubble factor for analysis. And we can also, for very large values of asymmetry, expand this scale factor here. And we find that not only there is a classical contraction, but also a quasi-de expansion right after the bounce. So this is very interesting because it has been found for essentially only perfect fluid as a matter of content. There is no exotic field here. And we have been considering recently the quantum potential. It takes on this form here. But for large values of asymmetry, it turns out that it is independent of the parameter y and reduces to a scaled-down version of the symmetric case for the quantum potential. So here is the asymptotic behavior of the quantum potential for large asymmetry, and the same asymptotic process happens for the perturbation potential, which we have been considering here in preliminary analysis for cosmological perturbations. Both scalar and tensor ones will satisfy the so-called Muhanov-Sasaki equations. And if we take the initial condition for these perturbations as the adiabatic vacuum in the remote past, which is asymptotically flat, we can find by matching conditions at horizon crossing during the quasi-de expansion that these modes have a specific k-dependence, which can in turn produce a nearly scale invariant power spectrum for perturbations. Now, this happens only for radiation, which is very good, scale invariance, but also for radiation, this tensor to scalar ratio is extremely large, which is contrary to observation. So as future steps in our work, we'll try to work around this issue, probably using the curvature field, and also work on the numerical analysis and comparisons to confront with our previous estimates and possibly work on some possible variations of this system. So thank you very much, and that's it.